Organic production. So, hello everyone. Thank you for being here present. I'm going to present you the paper entitled "On the Role of Delayed Tolerant Networks and Contact Routing in Direct-to-Satellite IoT." So, this work was started by Sebastián Montoya. He's a student from Universidad Católica in Chile. He did an internship at INRIA under the supervision of Juan Freire, who is also my PhD advisor. And then we finished this work recently with the help of Sanders Espíritu from Concordia University. And we submitted the paper for this workshop. So I'm going to begin by introducing what is my research subject, which is not DTN or CGR, but it is satellite Internet of Things. So maybe you have heard about Internet of Things, the idea of having small devices, battery powered, low cost, to enable many applications for urban or rural scenarios, collecting data, for example, setting low-cost networks. So the idea is to enable satellite support for these IoT devices, especially for scenarios where we don't have access to a power grid, so we only have battery-powered devices, and maybe we don't have access to a gateway with actual power from the grid connection. So we may use satellites to collect data from IoT nodes. These IoT nodes may be in really isolated scenarios, might be desert or the open sea. So we may profit from low-cost satellites, for example, CubeSat, following the low-cost IoT devices, to collect this data and relay it to ground stations. So there are two main physical layer solutions for IoT devices currently in use. One is NB-IoT, which is supported by the 3GPP organization. And the other one, which is my focus, our current focus in our lab, is the LoRa, which is developed by Semtech. It's a proprietary physical layer, but it operates in GSM bands, so it's open. So basically anyone can set up IoT networks based on LoRa, and if you have a satellite in your backpack, you may deploy it and start your own free IoT constellation, IoT network with satellite support. Recently, there's also the new LoRa FHSS, so frequency hopping spread spectrum modulation, which was specifically designed for massive communication. So this is massive uplinks, potentially thousands of IoT nodes, and a single gateway collecting thousands of incoming uplinks from these IoT nodes. And there is a number of startups already starting this as a business model. We have, for example, Kinase in France, Lacuna is from UK, and I don't see it here, but also we have Fosasat from Spain, and a number of other startups also exploring both LoRa and NB-IoT solutions. So I really like this diagram from Juan. So here we can see the whole integrated space terrestrial network with IoT devices. So we begin with showing what is the typical terrestrial IoT scenarios, either urban or suburban scenarios, where we have the IoT devices connected to the gateways, as I mentioned. And typically we assume in IoT that the gateway is connected to the internet, so we can relay the messages from IoT to the network server and the application server directly. On the other hand, on the left part of this diagram, we include satellite supporting IoT, and we have many types or different solutions to provide satellite support to IoT devices. In the middle, we can see the one called indirect to satellite IoT. So here, the IoT nodes are still connected to the gateway on ground. And here we assume that the gateway is not connected to internet, but it has enough power to relay these messages to, for example, a geostationary satellite. And eventually this geostationary satellite is going to relay this message to the ground station, and eventually it will reach the application server providing internet support to these IoT devices. But what we're focused on is the scenario to the left, which is the direct-to-satellite IoT. So these small power devices, battery power devices, are able to connect directly to the satellites. And here we're using LEO satellites, a single satellite or a sparse constellation, maybe, or dense constellations. This is what we're going to study. And we may or may not have ISL links. So in case we don't have ISL links, the LEO satellite is just going to recover the messages and then forward them to the ground station node, to the ground station when available. So this introduces. So what we want to study here in this project is what is the impact of having inter-satellite links providing support for IoT devices. So now we may use ISL to relay these messages faster to the ground station and eventually the application server to provide support for our IoT application. So we're studying mainly these two types of constellation. We have the Walker Star and the Walker Delta. They're pretty famous. So we're basically basing our study in comparing these two type of constellations and trying to see which one will perform better for IoT support. We do this because in general, most research, as I mentioned before, is focused on a single satellite collecting massive amounts of communications. But what if we have more than one? So this is the study about. So we're exploring, as I mentioned before, the use of delay tolerant networks. And as I also said before, my main research focus is satellite IoT, not that much delay tolerant networks. So I'm going to profit that all of you are experts in DTN. So I'm going to fast forward a little bit this slide. The approach, what we're using is the contact graph routing. So we're going to have episodic connections between IoT and satellites or between satellites and ground stations. So we're going to use a networking algorithm based on contact graph routing. How are we going to simulate this scenario? We have a simulation tool for DTS IoT that we've been using in our lab at INRIA for the simulation of LoRa for IoT devices supported by satellites using LoRa. So basically we have the satellites, or satellites are going to be propagated using the SGP4 propagator. And the satellites are going to have connection to, of course, ground stations. And the ground stations, we assume that they're connected to the internet and eventually they will reach the network server. And on the networks, the end device side, so the IoT nodes, we're going to have our LoRa communication. And on board of the satellite, we're going to have an additional gateway for LoRa communication. And we provide the satellite the capability of ISL links and also ground station links. So what we actually simulate is in two steps. We're actually doing two simulations. The first simulation is for the contact plan simulation. We're basically set up our constellation, set up our IoT nodes, and we just run the simulation just to get the contacts. We build a contact graph, and in the second simulation, we're going to use this contact graph with the same nodes, the same position, starting position for the satellites, and we're going to start the traffic of from IoT nodes to the constellation with the already calculated contact plan. So this is a twofold simulation, actually. So these are the parameters that we're using for the simulation scenario. As I mentioned before, we're comparing the constellations Delta versus Star. We want to study, of course, ISL versus no ISL. And we chose to compare scenarios with 4 orbital planes against 8 orbital planes, while the number of satellites, we're going to increase it from 8 to 64 in step with 8 satellite step. And what else do we have here? We also have the ground station link data rate. We set it to 10 megabits per second. Also the inter-satellite link data rate, we set it to 1 megabit per second. For the ISL configuration, we're going to have intraplane, so across track, and interplane, so no, along track and interplane with adjacent planes, so across track. So we have 4 possible ISL links for a single sat. And we decided to use 5,400 kilometers. This might be long for an ISL range, considering that we have also the atmosphere, but this is, this for now is out of the scope of this work. And the ground station link range is 2,700 kilometers. So this is the distance from satellite to the ground, either ground station or IoT device. We're assuming also a 5-degree minimum elevation for communicating to the satellites. And the traffic model is going to be, we're going to set 10 IoT nodes, and we're going to set them spread around the Earth. And what are we going to do? Each IoT device is going to transmit 100 packets to every other 9 IoT devices. So in total, we're going to have each IoT device is sending 900 packets, and then we're going to calculate the average of these for metrics. So end-to-end delay or ISL transmissions. The bundle generation is during 15 hours, and then we let 9 hours of idle, no traffic, in order for all packets or bundles to arrive to destination. And lastly, we're using the revision 17 version of the contact graph routine. So this is how the scenario looks like in our simulator. For example, on the top, we have the star constellation with 4 orbital planes. We can see the planes in different colors. And here we can see, I don't know if you can see the black lines. We actually have intraplane. The intraplane is you can see the connection with the colors, and interplane with the black lines, ISLs. But on the bottom side, we have the Delta constellation with 4 planes. And in this case, we don't have the interplane satellite links. We only have the intraplane satellite links. And this is the cases when we set 64 scenarios. And also you can see the IoT devices with the purple dots, more or less spread over the Earth. I set them not in, as I mentioned before, in remote locations, but mostly in known cities, just so you can locate the cities better. But the idea is that these devices are going to be in remote areas. This is how it looks like with 8 orbital planes. So in star constellation, we still have the intraplane and interplane. And now in Delta, we can see that we managed to connect interplane with 64 satellites. So I'm going to start with the results comparing the scenario without intersatellite link against intersatellite link. So if we look at the left, we have the end-to-end delivery delay for Delta scenario using 4 orbital planes with and without intersatellite links. We can see that we have ISL links just when we have 8 satellites per plane. So in total, 32 satellites. Before, there's no enough, the distance between satellites is too long, so we don't manage to have intersatellite links. So when we have intersatellite links, we can see immediately the effect that we can decrease the delay, the average delay in the whole traffic the whole network, the whole traffic. So we have the average, and we have the maximum delay in the bar, the top bar. So we can see that we can decrease about 50% the average delay when using intersatellite links. On the right-hand side, we have the results for the star constellation. So in the star constellation, we have for 8 satellites, we already have the ISL links, as I mentioned before. But we can see that with intersatellite links in the star constellation, we can decrease from 200 minutes average packet delay to just 10 minutes. So this is a huge increase. But we don't see an improvement if we increase the number of satellites, not that much after 32 satellites. So that it's a thing. But we can reduce the maximum delay. So you can see that the maximum delay in the star is going to be just around 150 minutes, while without intersatellite links, it can be up to 700 minutes. So that's a lot of difference. Okay, so now we continue comparing Delta versus Star. So we already know that enabling intersatellite links is going to improve a lot the delay. It's going to decrease a lot the delay in our IoT network. But what about comparing Delta versus Star? Which one is better? So if we look at the left, we compare the 4 orbital planes of the star constellation versus Delta constellation, now both enabling intersatellite links. And we can see also, as I mentioned before, that the Delta intersatellite links appear after 8 satellites per plane. So here we see that on average, we have 40-minute delay per bundle for Delta and just 10 minutes delay on average for the star. So when using 4 orbital planes, star constellation is better for any number of satellites that we set in our 4 planes. And the hop count is the number of hops from the IoT device to the ground station. So the minimum number of hops that we can have is 2. So this is from IoT to satellite and satellite to ground station. But when we start using ISL, you see obviously that the hops is going to increase. And on average, the star has 2 more hops. So 2 more hops is more power consumption for the satellite, because now we need to send this data from satellite to satellite before getting to the ground station. So now we're comparing the scenario of 4 planes against 8 orbital planes. So to the left, again, we can see delta scenario comparing 4 planes against 8 planes. For the scenario with 4 planes, we see, again, the ISL links after 8 satellites per plane. But for the 8 orbital plane scenarios, we already have inter-satellite links, because of the distance is short enough to connect the satellites, as we assumed. So already with 8 satellites, so 1 satellite per orbital plane, we can achieve, this is like a round the Earth connection. So we can already decrease the delay a lot compared with the 4 plane scenario. And when we have 2 satellites per orbital plane, we can already decrease the average delay to under a minute. And the maximum delay is going to be just over 10 minutes. So this is a huge increase when using 8 orbital planes. But if we see the star case, the star constellation case, there's no much gain observed in the case with 8 orbital planes. Here is just a little bit better, a little bit lower the delay, but we don't see much gain. Maybe we can see that the maximum delay is decreased from 150 to more or less 70, 80 minutes when we increase the satellite number per plane, but the gain is not as evident as in the delta case. So again, we're comparing 4 planes against 8 planes, but now we're comparing the hop count. So the hop count, as I mentioned before, the minimum number of hop counts is 2 from IoT to satellite, satellite to ground. So we see that on average, we have 5.5 hops when we're using the delta with 8 orbital planes. And we observed it's more or less the same amount of hops for the star 8 planes. So this is more or less similar for both scenarios, comparing 8 planes star against 8 plane delta. Okay, but we're also interested in this metric, what we call the Dijkstra cost, because computing this routing algorithm is costly in terms of computation. As I mentioned before, the idea of satellite IoT is maintaining low cost, low power consumption, both in IoT and also on orbit or platform or satellite. So we also want to do the less computation possible, but we observe that it's more or less similar for all of the cases. All of the cases, I mean, star and delta with 4 or 8 orbital planes. And just the delta with 4 planes, it seems that it has lower computation compared to the other cases. So this brings me to the conclusions. So as I just showed, enabling inter-satellite links significantly improves the end-to-end delay for LEO constellations supporting the IoT devices on ground in the context of direct-to-satellite IoT. At the cost, of course, of having additional transmissions. We're going to have the transmission between the satellite, obviously the inter-satellite links, and the computation on board of the satellite for the routing of this packet. The star constellation offers a better delay on average when we are comparing the cases of 4 orbital planes against delta. The number of ISL hops increases after 8 satellites per plane, but there's no significant change in delay observed. But on the other hand, in the case with 8 orbital planes, we observe that the delta constellation performs much better in terms of delay against delta. So delta offers a minimum delay with the average of under a minute, just seconds per packet, when we have just 3 or more satellites per orbital plane. So the particular scenario that was best in terms of less satellites and less delay was the case with 8 orbital planes and 2 satellites. In this case, we observe a delay with less than a minute, just some seconds average delay, and the maximum delay is 10 minutes, which is fairly good for a typical Internet of Things application. What is the problem? That deploying 8 orbital planes is more costly in terms of launch cost than in 4 orbital planes. So that's also something that it needs to be considered. the last result, as I presented, there's no major difference in terms of computational effort for the networking in the different scenarios, delta star or 4 and 8 orbital planes. And lastly, the future work includes the trade-off study of intersatellite links and more ground stations supporting the IoT, direct-to-satellite IoT networks. So that's it. Thank you very much.
Do we have any questions?
Yeah.
Think that there's any kind of way to avoid doing some of the CGR from the end locations in that kind of a periodic situation where, like, something simple like send nearest orbiter instead of doing like a full CGR?
You mean from IoT to? Actually, I didn't consider that scenario because the main focus was using CGR in this context. So, but that's a good point. We didn't consider an alternative because, again, the focus was DTN over the.
I think your point is not running CGR in the IoT device, but running CGR on the satellite, right?
Yeah.
So, of course, you can do that. I mean, the thing is that like the greedy policy of sending the first satellite available is possible, but suboptimal, of course, right? Because not necessarily the next passing by satellite is the one that is leading you to the best route to the destination. So I guess you pay that. I mean, if you run CGR locally, you pay, but you get benefits. But I think it's an interesting trade-off to actually evaluate.
Sure. Yep.
Did you have any discussions? It's not covered on the paper, but do you have any discussions about how QoS would affect some of the results, especially in delay? Trying to understand what is absolute delay versus.
That's really specific to the IoT application that you want. So the delay is going to be closely related to the application. But yeah, we didn't study different the needs of certain applications. Of course, you have more critical applications where you want to decrease the delay. But as I just showed, maybe your constellation is going to be too costly because the main one of the main premises of IoT is keeping low cost and low power consumption. So, but that's really important. Let's observe. It depends on the application. Yes.
How precise are you can estimate the timings for your IoT devices?
For precise what? Sorry.
Precise fault do you have with devices? Have some margin like.
I'm not. Do you know?
Well, what's the question? Sorry.
So for instance, to know when to transmit the IoT device, you need to know when exactly.
You mean the clock synchronization? Yeah. Well, that is quite bad. If you use like commercial off-the-shelf devices, I think you have after 2 hours you are out of you are out of synchronism. But this is a different problem because there are synchronization ways. I mean, so that you at least every 2 hours you hook into a new satellite, you resynchronize, and you stay in synchronism. If you need to stay synchronized, but if you use LoRaWAN like class 8, for instance, you don't need synchronism. You just send the data whenever you want. Of course, if there is a satellite, it's get it. If there is no satellite, you lose it. So these are different options. Yeah.
Yeah. In the context of LoRa, above layer, the link layer, that is a whole problem to decide when to transmit, when is the satellite passing in the concept of like dumb IoT nodes that cannot do much. So it's a whole problem what you're asking, but it's a good question. Yeah.
Any other questions? Thank you very much.
Thank you.
All right, and with that, we are done just a few minutes early, and then we'll see everyone back in about 35 minutes, 40 minutes for the last session of the day.